This is our third video in our series on a lesson in factoring, and this video deals with special cases. You will need the class notes 14.6, not the key, and the class practice on 14.6. If you watched part 2, you've already printed these out, I hope. Okay, I'm going to talk us through a quick review of factoring. When we see something that requires factoring, our first job is to always factor out the greatest common factor if possible. The possible exception to this is if you have a perfect square involved, and then you want to be careful to see which is best, to leave it as a perfect square or to factor it. Our second step is to decide if any of our factors, any of our trinomials or binomials, have perfect squares involved. If so, then if there are two terms, are they a difference of squares? And it has to be difference. If they're a sum of squares, they're already factored. Are they a sum or difference of cubes? And then if any of those cases are true, you can use the formulas that correspond to those cases. The third question you ask is it a perfect square trinomial? And it could be a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. And if it is, use those formulas. So right now we are going to focus on these three situations. If it isn't any of these situations, then you ask, is the lead coefficient 1 in front of the x squared term, and then you use reverse FOIL, which we'll cover in the next video. If that coefficient is not 1, if it is 2 or 4 or negative 8 or anything like that, then you use grouping, and you also see if you can use grouping if you are given 4 terms and it's not a trinomial but it has 4 terms in it. But let's go ahead and get started with our special cases. First of all, we're going to look for these problems. Remember, all of our special cases require that there be perfect square trinomials in the first and last terms. Okay, here that's not a perfect square trinomial because there's no square root of 8. Here we have to do the greatest common factor, and what we're left with will not have a perfect square. Here 6 isn't a perfect square trinomial. Here we have p squared, which is, and we have 25, which is. So we're going to look at that one. And then here we have 49, which is 7 squared, and 9, which is, so we're going to look at that one. And then in the next one we have 8, which is a perfect cube, and then we have 64, which is also a perfect cube. So we're going to look at that one. Number 7, we do not have perfect squares. Number 8, we can factor out a 2, and we factor out a 2, we get 14 here, and that's not a perfect square. In number 9, we have 900 is not a perfect square, but first we factor out a 9, and so we have 9 times x to the 4th minus 100, and now we do have a difference of squares because x to the 4th is the same thing as x squared squared, and so the root would be x squared. In number 10, we don't have a difference of squares. In number 11, we're looking at cubes because this variable and this variable are cubed. 27 is a perfect cube and 125 is a perfect cube. And then in this one, again, we're pulling out a common factor, and what we're left with will not have a perfect square. Beginning with number 4, we notice that again, in the special cases, if it's a binomial, then it needs to be a difference of squares, sum of squares, or sum of cubes to use a formula. But this is a trinomial, so the only thing we're looking for in a trinomial is if it's a perfect square trinomial, which requires the first and third terms to be perfect squares. Well, the root of the first term is p, so p squared is a perfect square, and the root of the third term is 5, because 5 squared equals 25. So our question is, does 2 times, and then multiply the roots, 5 times p, equal 10p? So if these are equal, then we have a perfect square trinomial. And so then we use the factor a squared plus 2ab plus b squared, I said factor, I meant formula, equals, and then you add the roots, put parentheses, and square it. So in this case, we have p squared plus 2 times 5 times p plus 25. We don't really need the middle term anymore because we've determined it's a perfect square trinomial. So all we have to do is write down the answer, which is that this equals, and then you add the roots, just like that. Don't square anything yet. Put the parentheses and then square the whole thing. And that's all there is to that. Now notice you could have solved this using reverse FOIL, which we will get to, and reverse FOIL isn't hard, so that would have been fine, but sometimes they do have hard ones, like if you had 64p squared as your lead term and 125 as your final term, you would really want to use the formula. Okay, number 5. We look at number 5 and we see 49, which is the root of 49 is 7, and the root of z squared is z. The root of 9 is 3. So we need to ask ourselves if 42z is 2 times 3 times 7z, twice the product of the roots. And 7 times 3 is 21 times 2 is 42, so we do have 42z. So that checks. And we can put a check mark and ignore the middle term, except for this minus sign. So now all we do is we put the first term, it's hard to do 7's and z's, and then we put the second root, and then instead of a plus we put a minus there to correspond with this minus. Then we put parentheses and we square it. So let me write it down here. Boy. 7z minus 3 squared is the solution to that. And if you doubt this, go ahead and FOIL 7z minus 3 times 7z minus 3, and you'll see you get this. Okay, in this problem, we have a cube here. We have a binomial. So we want to know if it's a sum or a difference of cubes. It can only be a difference of cubes. Now, before we started taking the test, we wrote down our formula for the sum of cubes. There's a cubed plus b cubed, and here's a cubed minus b cubed. And let me give you a refresher on remembering these formulas. You have to remember that it's going to have an a, b, an a squared, ab, and b squared. In both cases, those are identical, those parts. So then you need to decide what your operators are. The last one's always going to be plus, and then the first one is going to be whatever is here. So it's plus here and minus here, and the second one is going to be the opposite of that. And there you have your formulas. The next thing you need to have written down at the beginning is a few of your cubes. You don't have to go very far. You might go a little further than that. But here are your cubes, which you can crunch out on your calculator or memorize. Okay, so now we look at this problem and we look at 8 and see 8 has a cube of 2. So underneath we write 2x is the cube root of x cubed. And for 64, we see that it corresponds to 4 cubed, so we write a 4 here. So A is going to be 2x and B is going to be 4, and we're going to use the second formula because it's a difference of cubes. So all we do is write 2x and 4. So everywhere there's an A, you write a 2x, and here's an A, and then everywhere there's a B, you write the 4. So let's go ahead and write that correctly. We have 2x minus 4 times 2x squared is going to be 4x squared plus 2x times 4 is 8x plus 4 squared is 16. Okay, but you're not done. You need to look at this and see, is there a common factor? And there is. There's a 4 all over here, and there's a 2 here. So we're going to pull out the 2 from the first term. That leaves us with x minus 2. And then we're going to pull out a 4 from the second factor, and that leaves us with x squared plus 2x plus 4. And then the only thing we have left is to multiply the 2 times 4 to get 8. And then we are done. We said we would look at number 9. So we look at number 9 and we see that we have an x to the 4th term, and that may throw you at first, but then you think, okay, is x to the 4th a perfect square? And it is. It's a perfect square of x squared. So it's x squared squared equals x to the 4th. And so to decide if it's a perfect square, you just take the 4 and divide it by 2, and if that works out, then you use it. And we have a 3 squared here, but we don't have a perfect square here. But is there a common factor? And there is. So before we do any of this, we pull out the common factor, and we're left with x to the 4th minus 100. And now we do have perfect squares. We have x squared squared minus 10 squared. And we have our 9. Don't forget our 9. So we write down 9, and then we're going to use the formula for perfect squares, which is that the difference of squares equals the sum of the roots times the difference of the roots. Okay, the roots are x squared and 10, so we're going to have x squared plus 10 and x squared minus 10. But we're not done. We need to make sure nothing in the parentheses is factorable. So there are no common factors. So now we ask ourselves, we have binomials here. We know that the sum of squares is not going to be factorable. The difference of squares is, but is this a perfect square? No, it is not. So then we are done. That's our answer. And the last special case we have in this page is number 11. If you look back at your cubes table, you'll see that the root of 27 is 3. So we have 3a as the cube root of our first term. The root of 125 is 5, so we have 5b as the root of our second term. And we need to remember that a cubed plus b cubed, and let's use x and y so that we don't confuse this a and b with our formula. So we need to write down the formula, which hopefully you've written down at the beginning of your blue book. So you have x cubed, and it's going to be a sum, and we know we're going to have an x and a y, an x squared, an xy, not a 2xy, just an xy, and a y squared. We know the last one's going to be plus, and we know that since it's a sum of cubes, we're going to have plus in the first place and minus in the second place. So that's our formula. And now we just plug in 3a everywhere we see an x. So we write 3a squared and 3a here for x. And then we write a 5 everywhere, 5b everywhere we see a y. So there's 5b. And then we write a 5b here and a 5b squared here. Now you're going to want to use brackets around that because you have a lot of parentheses inside. So let's rewrite it. That equals 3a plus 5b. We don't have to do anything to that because there's not a common factor. And then here we have 3a, all of that squared, which gives us 9a squared, plus 15ab plus 25b squared. And then we see if we have any common factors left. Well, there's a 3 that goes into these, but it doesn't go into this. There are no other common factors, but there is a perfect square here and here. So does this equal 2 times this and this? No, it doesn't, because 2 times anything is going to be an even number, and that's an odd number, so we don't have to worry about that, and that means this is fully factored. Now turn to your 14.6 class practice, and I want you to circle the numbers of any of the special cases, because it's very important you begin to identify these things. So what you're looking for are perfect squares or perfect cubes, and you're only looking for perfect cubes if you have variables that are cubed. Okay, so pause the video and do that, and then when we come back I'll show you the answers. Okay, the ones to circle are number 2, and you might think number 5 because the first and third terms are perfect squares, but it's not a perfect square trinomial because when you multiply the roots by 2, which are 2 times k times 4, you get 8k, but the middle term is 6k, so that means it's not a perfect square trinomial. And then number 7 is a perfect square trinomial. Number 8 is a difference of squares. Number 9 is a difference of cubes. And number 10 is a difference of cubes. We worked 9 and 10, except the ones we worked were 9 was a sum of cubes and 10 was a difference of cubes. So you can work those if you like, but I'm not going to work them because we worked similar problems. But let's go ahead and work the rest of them together. Actually, I would like you to again pause the video, and we'll start with this one. So I want you to work this problem and then come back. Alright, here's the key to this problem. You decide what the roots of this is. It's 9x, and here the root of 16y squared is 4y. You turn to the formula you wrote down before you began the test, difference of cubes. You add the roots and subtract the roots. So here's the original problem. Here it is rewritten with its roots, and then you add them and subtract them, and that's your answer. Now look at number 7 and go ahead and do that on your own. Here's the key. On number 7, your first term, the root is 2p, and your third term is 7x. You have to test to see if this is a perfect square trinomial. So you have to see 2 times the product of the roots. 2 times 2p times 7x. Does that equal this? And it does. Now be careful, here you have 2p. It would be easy to forget that you're having to multiply everything by 2, so don't forget that. So you will want to have written down your formula at the beginning of your blue book so that you can refer to it. Here you have something in the form of a squared plus 2ab plus b squared So all you have to do is write down the sum of your roots, parentheses, squared. And that's your answer. In this problem, we have two things subtracted. It's not a difference of cubes, but is it a difference of squares? So see if that's true and go ahead and pause the video and work it out and then come back and check your answer. Here is the key to the first part of the problem. Okay, you begin by breaking up z to the fourth into z squared squared. 4 divided by 2 is 2, and that's where your other 2 goes. And then 81 is 9 squared. So you have a difference of squares. You look back to see your difference of squares formula, and then you plug in z to the fourth for A and 9 for B. So here's the problem restated. Here it is with its roots, and then you write the sum of the roots and the difference of the roots. Z squared plus 9, z squared minus 9. What you have to be careful of in a problem like this is, can you factor it further? So you know you can't factor z squared plus 9 further because the sum of squares is not factorable. But if this is a difference of squares, you have to factor it. And 9 is a perfect square, 3 squared, and z is also a perfect square, so you have z and 3 here. So you're going to factor that further by adding those roots and subtracting the roots. So we go ahead and come down over here and write the first term that we're not going to do anything with, and then add the roots and subtract the roots. And that's the end of that problem. So that concludes the special cases part of the video series. Let's go on to the next video to look at the case of reverse FOIL.